not necessarily going to back up. This is a topic that I'm moving into. So it's an opportunity to kind of tell you what it's about and some of the hurdles that I'm hoping to contribute to, ways that we can get over those hurdles. Now, it's kind of typical when you're starting to talk about industry and steel production that you go into Google Images and you say, I need an image that shows lots of smoke and chimneys and pollution. This is a little bit more. This is where I grew up. This is Teesside in the northeast of England, which, when I was growing up in the 1980s, had the second biggest steel industry in Europe and the largest chemical manufacturing industry in Europe. It's a very industrial landscape, which led to this term smoggy. So smog is this mixture of smoke and fog. So people from Teesside are known as smoggies because the term relates to the area's notoriety for its high levels of pollution from local industry, which resulted in a thick smog that often blanketed the region. You see further down here, smoggy has since been adopted as a term of pride by many residents of Teesside. Well, okay. I think that's mostly to do with the pride of the kind of industry heritage of people on Teesside. But so on the one side you've got the pollution, but on the other side you've got what that brings to the local economy in terms of jobs and manufacturing and so on. So a few steel facts. These are from the World Economic Forum. We currently have no scalable substitutes for steel. 95% of metal and alloy production globally is iron and steel, and there's no way that we can readily substitute that. So problem is, it's a highly energy intensive process, and more than 85% of that energy is coming from fossil fuels. Now, on the plot here, you can see how steel production has changed in terms of millions of tons since 2000 through to 2023. Although there's a bit of a plateau here due to COVID, steel demand has doubled since 2000. It's projected to rise another 30% by 2050. So steel is not going anywhere, but we just need more of it. And going back to the previous slide, it's a very important component of the economy. So iron and steel industry is $3.7 trillion in global revenue annually. And of course, that's bringing jobs, so on. So we need steel. So this is a graphic from the Minerals Research Institute of Western Australia that I'm going to be referring to quite a lot. It's the iron ore to steel pathway. It should be pretty obvious what's going on here, but we go from our iron ore source through things like drilling, blasting, crushing and screening, which is sieving, and then the lump material gets fed into the iron ore feedstock, which goes into producing iron. Lower grade material goes through this process called beneficiation, which is simply increasing the iron content of the ore. And then along with fine material, it gets agglomerated into larger pieces and fed into this iron ore feedstock. We can then go through two routes, putting the iron ore feedstock into a blast furnace with coking coal, which produces carbon monoxide, acts as a reducing agent, takes the iron oxide, converts it into iron, or in this case, what's referred to as pig iron, and then it goes into a basic oxygen furnace to remove extra impurities like carbon before being turned into steel. The alternative route is through a shaft furnace to produce this, what's called direct reduced iron. This is maybe using something like hydrogen or even carbon monoxide as a reducing agent. That doesn't actually melt the ore, so it kind of comes out, it's a bit spongy, not very stable, so often it's briquetted to make it into a kind of more stable pellet before it's melted in an electric arc furnace. And if you wanted to, this is the point where you can add scrap steel in as well, and it's just melted in the electric arc furnace before going into casting and so on. So both of these routes, whether we're going along the top or along the bottom, are high energy, produce a lot of fossil fuels. So it isn't as though there is one high and one low, they are both high. So we should probably refer to this as high and higher, as you'll see in a moment. So like I said, more than 85% of the energy comes from fossil fuels. So what we've got, time along the bottom, intensity is the number of gigajoules of energy used to produce 1 ton of steel. So you can see since 2000, it's coming down a little bit. It's the orange line here. basically it's not changing very much. Whereas the demand, so what's actually providing that energy, you can see the vast majority of it is coal, a little bit of gas, some electricity, and then we've got trivial amounts from things like bioenergy. So this is fossil fuel intensive. And I'll come into how that breaks down in a moment. So for those different steps that we saw earlier, all the way from getting the iron ore out through to shipping steel, this is the associated emissions in tons of carbon dioxide per ton of steel produced. So we've got drilling and blasting through to shipping. You can see really the elephant in the room here is the iron making. That's where pretty much all the emissions are coming from. Everything else is small on that scale. So when we look at steel production in different countries, and again, carbon intensity in terms of tons of CO2 per ton of steel, we can see China and Brazil, 2.4 to 2.8, UK is 2.2 to 2.3 tons of CO2 per ton of steel. This is where they are going along this top route here. And they're using coking coal, a blast furnace, and a basic oxygen furnace. Now, when you get to Brazil, they've got that number down a little bit because a lot of these stages that are using electricity, they're able to do that from hydroelectric. So that renewables source of electricity brings down the emissions, but you can see using alternative sources of electricity, you're only going to bring it down so much because it's the electricity is not where the emissions are actually coming from. By the time we get to Mexico and, for example, BlueScope, they're using electric arc furnaces. So they're following, whoops, wrong way. They're following this route down here of direct reduced iron and electric arc furnaces, and they're able to bring those emissions down. Emissions are still high, though. When you look, it's still 1.6-ish tons of CO2 per ton of steel. So again, this is from the World Economic Forum, just thinking about these two pathways. The pathway along the top, where we've got coking coal in the blast furnace versus direct reduction along the bottom. 70% of the steel produced globally is through this blast furnace, basic oxygen furnace route. That's the top route. And then we're talking about CO2 emissions of 2.3 tons per ton of steel. So again, this is the really fossil fuel heavy route is the one that is dominant in terms of iron and steel production. The alternative pathway along the bottom, which was direct reduced iron and electric arc furnace, CO2 intensity is lower, 1.4 tons per ton of steel, but that's only about 30% of production. If you're just recycling scrap by melting it in an electric arc furnace, this comes down to really just the electricity that you need to use to heat the furnace, about 0.7. Okay, but clearly with that increasing demand that we saw projected by the World Economic Forum, we're not going to have enough scrap in the future to satisfy all our steel demand. So we're always going to have to be producing new steel or primary steel. So let's look at what's happening in this blast furnace. So, like I said, we've got blast furnace, we're using coking coal to produce pig iron, which is then goes into the basic oxygen furnace to remove things like carbon before going into the steel production. So at this stage here in the blast furnace, that's using about 770 kilograms of coal to produce 1 ton of steel. And this is actually metallurgical coal, so that's heated to about 1,000 degrees C to create coking coal. And then the coke is added into the blast furnace along with the iron ore. It's heated up to around 2,000 degrees C. And that production of carbon monoxide from coking coal acts as the reducing agent. So what you get is the temperature liquefying the iron and the carbon monoxide doing the reduction, so you're outputting this liquid iron. So as you can imagine, this is pretty heavy in terms of its fossil fuel footprint. Now, we think of Australia as a large exporter of iron ore. It's also a very large exporter of metallurgical coal as well, that goes into making coking coal. So maybe these numbers are a little bit too small to see, but the countries in blue are the top 5 exporters of metallurgical coal, and the big steel producing countries, China, South Korea, Japan, India, and so on, are the big importers. Now, you may not be able to see the numbers here, but these are, in terms of exports from Australia, these are tens of billions of dollars. So we're not just talking about iron ore export in terms of steel production, we're also talking critically about metallurgical coal so that coke can be produced. So this is big money for Australia. Okay, going back to Teesside, where I grew up, this is coking ovens. So they produce their own coke on Teesside in preparation for the steel making process. I have vivid memories of this as a child because it would stink. And I'd always say to my mother, "What's that smell?" And she said, "Oh, it's the coking ovens. They're making coke." So it's a really pretty horrible smell. So when we look at greenhouse emissions in terms of sector, again, this might be a little bit small across the top. This is 2016. Global greenhouse emissions were about 50 billion tons of CO2 equivalent. And then this analysis split everything down into different sectors and where it's being used. Okay. So what you can see here, is that one on there? Just move the mouse across. Yeah. Iron and steel is 7.2% of global CO2 emissions. My understanding is that in terms of a single production industry, it has the biggest carbon footprint. And we can compare it to other things that we're naturally concerned about, things like aviation, 2%, shipping, around 2%, iron and steel, like I said, it's around 7%. And based on just kind of a bit of Googling of numbers, it would appear, at least, if we could take carbon emissions out of iron and steel production, that would be equivalent to removing the greenhouse gas contributions of India. Okay, it's that kind of scale. And India is the 3rd biggest emitter of greenhouse gas. So this is a significant carbon footprint in terms of a resource that is absolutely essential. And of course, the industry is aware of it. So this comes from the World Economic Forum, Steel Industry Net Zero Tracker. You can see a number of the statistics that we've talked about already. So contribution to greenhouse gas emissions is about 8%. Expected demand increase is around 1.4. Fossil fuels used in the mix, greater than 85%. Current low emission production of steel is less than 1% of the steel is produced using low emission technology. But like I said, this is on the radar. So there's a target to 45% reduction in primary steel emissions by 2030. When you think about it, it's only 5 years away, as scary as that might sound. Net zero by 2050, and 70% of large steel companies currently consider climate change in their decision-making train. So people are striving to try and improve this situation. So we talk about green steel. It's really just decarbonized steel. So to put it in one kind of sentence, green steel is still produced using processes that significantly reduce, or if we can achieve it, eliminate carbon emissions completely. And a lot of work is being done on this already. We've got partnerships being formed, for example, the India-Australia Green Steel Partnership. The idea between this one is that, in this partnership, is that a number of hurdles that are faced to produce green steel are shared between India and Australia. So it makes sense to collaborate on these problems and try and solve them. So what does green steel involve? Well, I talked about the left-hand side of this plot already. We can take some iron ore, which is an iron oxide, for example, hematite, in this case, Fe2O3. And normally by putting it in that blast furnace with the coking coal, we're reducing the iron oxide into iron, but the byproduct of that is CO2, even though we produce the iron that we need. And the alternative pathway for green steel is, again, we start with our hematite iron ore. We do reduction using hydrogen, and then in principle, the outcome of that is water and iron, which you can then subsequently melt in the next step of the process. So clearly, this would be particularly good if we can get this side working and start producing steel effectively with zero emissions. So when we go back to the Minerals Research Institute of Western Australian kind of chain, green steel production looks a little bit different in terms of pathways. What we're doing is replacing everything where we had before, where we had greenhouse emissions, we're replacing it with either renewables or alternative technologies. So things like drilling and blasting, excavating and hauling would be powered by green ammonia and green hydrogen, which I'll talk about in a minute. Where you need electricity, that's coming from solar or wind power. And you can imagine, you know, if you're out in the Pilbara, you could build a very big solar farm. You've got pretty consistent winds along the west coast of Australia that could be generating power. Once we get into this shaft furnace where we're doing the reduction, this is where the coking coal is replaced with green hydrogen to reduce the iron ore into iron. And then the furnace is going to be heated with renewable energy, electricity from solar and wind, rather than heating it using coal. So this is the plan for an emissions-free green steel production. But maybe in Australia, we don't need to worry about that. I mean, for Australia, apart from this small amount of steel production, the value chain kind of stops here, where iron ore feedstock is produced and then it's exported overseas. So Australia is producing 35% of the global iron ore supply and exports 55% of the global metallurgical coal supply, but is only producing 0.3% of global steel supply. So maybe Australia needs not to be focusing on green steel, but rather green iron ore production. And in which case, things become simpler. I wouldn't say they're simple, but they are simpler. But we're really just looking at replacing diesel trucks, for example, with trucks running on hydrogen, and we're using renewable sources for electricity rather than fossil fuels, and then not really thinking about the actual steel production because that can be done overseas. So maybe the pathway to green iron ore production is, like I said, it's not simple, but it's certainly simpler. So just briefly, what would it mean to produce green hydrogen, green ammonia? These graphics make it look deceptively simple. Like all of these technologies, they sound simple when you describe them in a few sentences, but there's a large number of hurdles to actually achieving them. So one example is production of clean hydrogen, for example, through electrolysis of seawater. And you say, oh, it's simple. We get renewable energy. We use that in electrolysis and we produce clean hydrogen. Of course, it's much more complicated than that, particularly when you start trying to do it at scale. But one of the key things here is that this need for clean hydrogen, for example, for running transport, is not unique to iron and steel production. It's going to be something that's used to decarbonize in industry globally. So there's a lot of push to do this. Even with those hurdles, hopefully it's a problem that can be solved because it's such an important problem to solve in terms of decarbonizing all industry. Similarly, green ammonia, the advantage when you combust ammonia in a fuel cell, all it's doing is producing water and nitrogen. And the key thing is it's easier to transport than hydrogen. The pathway's similar. Okay, we're taking water, we're performing electrolysis to get hydrogen. We're also taking air pulling the nitrogen out of it. All of this is driven by renewable energies, Haber Bosch process, green ammonia. Again, sounds really simple. There's big hurdles to do it, but when the whole of industry needs these kind of products, then that's a lot of clever people working on a difficult problem, and hopefully it could be solved. And some of this technology is already in place. This is an example of the Komatsu PC8011 electric excavator. So mine sites are already using electric excavators, electric vehicles, and so on. Of course, what this relies on is that the electricity that is being used to power them is actually coming from renewable sources. If it isn't, then you still have a fossil fuel footprint. But at least these things are energy agnostic in terms of they will take electricity from wherever it's coming from. You don't need to fill it up full of diesel in order to get it to run. So some of these technologies are already available, and it's about being able to provide the renewable energy sources to get them to run. So thinking about steel production, this is kind of a recap of what I showed earlier. We've got iron ore producers, with Australia dominant here, about 35% of the market. And you can see other big producers like Brazil and China and India and so on. But by the time we get into top steel producing nations, dominated by China, we don't even see Australia. Okay, so Australia is about 50th in the world in terms of steel production, even though it's the main exporter of iron ore and metallurgical coal. So where would the benefits be in Australia starting to produce green steel? Well, there's another industry that is clearly a booming industry, but is this the right time to join it? What I've got here is a plot of average blast furnace age in years for different steel producing locations against the amount of crude steel that they produce as a percentage of global production. China's dominant. We've got other places up here. And of course, this blast furnace is a significant capital cost in terms of building the infrastructure. And the blast furnaces have typical lives of around 40 to 55 or so years. So we're now at the stage where a number of significant producers will have to renew that infrastructure. And typically, since they're now being forced to renew that infrastructure because it's come to the end of life, they're starting to replace it with green steel production where possible. There's many reasons for this. Clearly, the demand for green steel is going to go up, particularly if there becomes a tax on carbon and so on. And that would actually put the price of green steel lower than traditionally priced carbon. At the moment, if you just did it, in terms of cost of production, it's more expensive. But the technology, I'm sure, will bring that down. And like I said, if they start taxing carbon, then green steel ultimately could become cheaper than traditionally produced steel. So a lot of these countries are now moving towards replacing their infrastructure and thinking about replacing it with green steel. India, well, their blast furnaces still have a pretty long life, so maybe they're not going to be replaced. The interesting one is China. Up here, you can see, on average, it's got the youngest blast furnaces, but they're still investing in green steel infrastructure. They've got sufficient capital to actually start building green steel production, even though their blast furnaces still have decades in front of them before they reach end of life. So maybe with this kind of resetting of the industry, this would be the time for Australia to join steel production. Now, obviously, I'm not going to make that as some kind of recommendation to the government because I'm not an expert, but it seems that kind of thing is in the wind. When we look at Australia's national science and research priorities, the new ones that were just published, one of the priorities is transitioning to a net zero future. And I've just highlighted this sentence here. We'll develop and use new technologies, materials, and processes to change energy generation and storage, heavy industries, and agriculture. Well, apart from the agriculture part, this is pretty much green steel. Okay, you're going to have to work out how to generate energy from renewables, you're going to have to store it. You're moving it over large distances, for example, green ammonia. And that heavy industry that you have to decarbonize is what we've been talking about. So this is clearly a priority nationally. And the government is providing support for this. So this is from the Trade and Investment Commission. Again, I've highlighted a bit about the money. So up to $3 billion, $15 billion fund has been set aside to finance renewables and low emissions technologies. This includes funding for green steel and iron. So this is something that the government is taking very seriously and backing it up with funding as well. And it isn't just at the government level. Also at the industry level, there was this announcement in February. This is just an article from the ABC. BlueScope, Rio Tinto and BHP join forces on plan for low carbon steel future. And there's a couple of interesting statements in this ABC report, which are kind of going to be the focus for the rest of my talk. The partnership will attempt to create technology that will allow the Pilbara's low and medium grade ores to be used. We'll come on to what that means in a minute. And this direct reduced iron technology is also dependent on high-grade ores, and Australia's ore supply in the Pilbara is disadvantaged by high levels of impurities. And this is going to have domestic and international implications. So maybe we're already talking about a complicated problem. Maybe this is an additional hurdle. So what does all this mean in terms of ore type, grade, and gangue? So this is an example of an iron ore reserve. And, we can be talking about different types of minerals here. Typically, iron oxides or iron oxyhydroxide. So we've got hematite, goethite, magnetite. I'll talk a little bit about those in a moment. And each one has different steel making processes and energy requirements. So some are better than others. The grade is just the iron content in the iron ore. But that's important because the higher the grade, it means the less processing it needs and lower energy costs. So if you can get high grade ore, that's fantastic. The gangue is the non-iron based impurities that you want to remove so that you can increase the grade of your ore, make it easier to process, and so on. And this is a report from the Institute for Energy, Economics and Financial Analysis. Got a rather kind of worrying title, Iron Ore Quality, a Potential Headwind to Green Steel Making. And again, I've highlighted here, however, insufficient supply of suitable iron ore is a potential challenge to a global shift towards zero emissions DRI processes. Again, that's direct reduced iron. So it looks like the iron ore we have may not actually be that suitable for green steel production. And for the technology as it stands at the moment, so this using hydrogen as the reducing agent, you're going to have to work with ore that has an iron content above 67%. And when we look at this plot of production of iron ore versus the percentage of iron, what we can see, the greater than 67% that's suitable for green steel is this little bit here. What's that, maybe 5%, maybe less. Everything else is at too low a grade to actually be used for green steel production. Hence these headlines on the ABC and so on saying that Australia may be disadvantaged because of the quality of its iron ore. So this is a real problem. And this is where I'm hoping to be able to contribute something to solving that problem, in that we need to go through a process of beneficiation, which is really just increasing the iron content of the ore so that it will then work in green steel production. And one of the techniques for doing this is so-called magnetic separation. What you're really looking to do is find any physical property that contrasts the iron-bearing minerals that you want to the gangue that you want to get rid of. And that provides some means, that contrast provides some means to actually separate them apart. So for example, that could be density, in which case you could use some gravity-based techniques to separate them. The other one, of course, we're talking about iron minerals, is their magnetic properties. So just to give you an example, I've got a movie here. We've got a collection of iron oxide particles suspended in a fluid. Is this going to work? Yep. And then, not surprisingly, if we put a magnet against there, it pulls the iron oxide particles towards it. So this is magnetic separation. Now we need to do is scale that up to industrial scales, which of course the technology exists. It's now a question of how to optimize that technology. So the overarching aim is to concentrate your mineral of interest, in this case an iron-bearing mineral, remove the gangue based on differences in magnetic property. So this is a cartoon of what's called a LIMS, so a low-intensity magnetic separator. And what we have is the iron ore fed in as a slurry here and flushed through the system. And then we have a set of magnets that are fixed in position. But around those magnets, there is a rotating drum. So if you have an iron bearing mineral in the slurry, it has an attractive force towards the magnet. It gets stuck on the edge of the drum. It gets rotated around here until it meets the edge of the magnet where the magnetic field drops away. And then it's no longer attracted to the drum and it falls into this magnetic concentrate. For the non-magnetic particles, of course, they're not feeling any attractive force here, so they get flushed through the system. Because this exit is higher than this exit, they tend to get flushed through into the non-magnetic component. So it's quite a straightforward concept, but the questions around it, for example, how strong should these magnets actually be in order to make sure you get what you want to get? We tend to talk about these minerals as being non-magnetic or magnetic, but in fact, all minerals are magnetic. It's just a question of how magnetic. So how are you going to set the field in here to make sure that you get out what you want and leave behind what you don't want? So if we allow myself one equation, so if we kind of look at what's controlling this, the attractive force acting on a particle from the magnet is a combination of what's called the magnetic moment. That's just really how magnetic the particle is. That in turn is a function of how strong the applied magnetic field is. Okay? So that's just kind of a fundamental property of a given particle. And the force is also dependent on the field gradient within the separator. If the field, the magnetic field, was uniform, there wouldn't be any attractive force at all. So you need a non-uniform magnetic field, which is just represented here. And in fact, in some separators, they really play on the field gradient part. So this is what's called a WIMS, a wet high-intensity magnetic separator, and they generate the magnetic fields within these magnetic cores, and because they're all spiky and they've got these irregular shapes, they can generate really strong field gradients. So they pump up this term here, and therefore increase the attractive force. So there's different ways of approaching this. Of course, there's some very clever engineering that's gone into building these systems. Now, fortunately, here at RSES, we know some things about the magnetism of rocks. This is the Black Mountain Laboratory that was built in 1964 on the, it's in a quarry on Black Mountain. We still use it every day. The original paleomagnetism lab was based on campus where biology is now, but you have a problem that when you, with instruments measuring very weak magnetic fields, if, for example, somebody drives past in a car, you're actually just measuring the car driving past. You're not measuring the piece of rock that you're interested in. So you have to move to what we call a magnetically quiet environment. And Black Mountain is such a place. Now, the field of rock magnetism is closely allied to paleomagnetism, but it's based more on the mineral physics of why certain things are magnetic. And this grew side by side with paleomagnetism. So this is kind of the foundational book by Nagata in 1961, just called Rock Magnetism, where kind of the basis of rock magnetism is you're characterizing magnetic mineral type, concentration, and size in geological materials. The reason you want to do that is that paleomagnetism was coming up with these hypotheses, like the Earth reverses its field reverses its polarity, which is useful for dating things. The continents appear to be moving according to the paleomagnetic evidence. So what you needed to understand was how those signals were actually formed. If you were going to assume they were reliable and that you could infer continents moving, the field is reversing polarity, you need to understand how the signal is actually formed and preserved in the rocks. And this was the birth of rock magnetism. So we can now use the equipment that we have. So this is an instrument down in the J4 basement. It's called a quantum design MPM magnetic properties measurement system. If you walk through the basement in J4, you'll hear it because it's got a very loud pump, because the system is operating with liquid helium, so it's cooled down to like 2.3 Kelvin. And it uses a superconducting magnet to generate very large fields up to 7 Tesla. But what this boils down to is we can measure magnetic moments of materials that are needed to understand what's happening in a separator. We can measure them with this instrument. So we can then inform what the expected magnetic forces are, what kind of fields you need to be setting in order to pull one thing out, leave something behind through this rock magnetic analysis. And of course, it's more complicated than that, but this is kind of the basis for it. And this is where often there's a disconnect between mineralogy and magnetic properties. So we've got iron oxides like magnetite and hematite, we've got goethite, which is an iron oxyhydroxide, and then we've got various gangue minerals. Now, even if somebody was able to tell you, oh, this bit of ore is made up of this percentage of magnetite, this percentage of hematite, and so on, you would struggle to actually work out what the magnetic moment is as a function of the field, because this is controlled by a variety of factors beyond simply the mineral composition. And this is where rock magnetism can really help in that design of separators. So I want to give you just a few examples of how these magnetic properties can change and the kind of thing that you need to think about if you're trying to optimize the configuration of your separator. Maybe so that this first case doesn't link directly to that, but it's just an example of how magnetic properties can change when mineralogy doesn't. Okay? So this is an example for magnetite, and it's so-called relaxation time. So you'd be familiar with the idea of paleomagnetism. You get some rock or lava, it's hot, it cools down, and as it cools, it preserves a record of the direction of the Earth's magnetic field. We can then come along hundreds of millions of years later, we can measure that direction and make a plate tectonic reconstruction, whatever. Now, if we were to take that record of the Earth's magnetic field preserved in that bit of basalt and store it at absolute zero, then that record would remain exactly the same forever. Problem is, of course, we're working at ambient temperatures. So even though it's recorded the Earth's magnetic field, there's this thermal activation of the magnetic lattice within the crystal that slowly works to randomize that magnetic signal. And once it's randomized, or the amount of time it takes to randomize, is what we refer to as the relaxation time. So you can see this is for magnetite particles. If I take a magnetite particle in nanometers with a width of around 17 or 18 nanometers, that paleomagnetic signal would actually be randomized in 100 seconds. Obviously, not a lot of use for paleomagnetism. By the time I get up to around 23, 24 nanometers, that paleomagnetic signal would be stable for 1 billion years. So in the space of a change of 5 nanometers, the properties of this magnetite particles have changed from them not being able to hold a stable signal through to them being able to hold a stable signal for 1 billion years. Okay? And somebody simply saying this is magnetite does not tell you what its magnetic properties are going to be. Similarly, with grain size changes, this is magnetite. This is work done by Adrian Muxworthy at Imperial College London. It's a numerical model of what the structures of magnetic particles look like as you change the size. So these are magnetite particles, 50 nanometers through to 1,000 nanometers. They all have the same shape. The only thing that's changing is their size. And the way that they're modeled is to split the crystal into a collection of elementary dipoles, basically just splitting it up into a load of tiny magnets. And then you work out what the lowest energy state for that particle is using this finite element approach. So what we can see at 50 nanometers, all our little arrows are basically pointing in the same direction. This thing is what we call uniformly magnetized. Okay? All these elementary dipoles are pointing the same way. Get up to 80 nanometers, and suddenly this thing, you can see the arrows here are corkscrewing around, forming what we refer to as a vortex of spins that goes through the crystal. It's doing this in order to minimize its overall energy. Okay. By the time we get to 300 nanometers, the energy minimization has actually split the particle into different zones that we refer to as domains, and the domains will be magnetized in different directions so that they cancel each other out. Okay. Again, this is just a strategy for lowering the energy of the particle. By the time we get to 1,000 nanometers, again, you can see these domains in blue much more clearly. So the only thing we're changing here is particle size, but the moments of these particles as a function of field are dramatically different. Again, somebody saying, I have magnetite particles, doesn't actually tell you very much in terms of magnetic properties. Final case, this is where things get really interesting, is particle-particle magnetic interactions. So in a separator, you can imagine I've got this slurry, it's full of magnetic particles, but those magnetic particles are not just subjected to the magnetic field produced in a separator, they're also subjected to each other's magnetic fields as well. This is work by Richard Harrison at the University of Cambridge, and what he did was he got this section of rock, so you can see this 200 nanometer scale here, and this has got regions of magnetite in it, which are obviously highly magnetic, but it's also got non-magnetic regions in pink, which is this uvo-spinel rich regions. And then he used a technique called off-axis electron holography in a TEM that allows you to actually image the fields of these particles. So this is equivalent to the experiment we all do in school, where you take a bar magnet and you throw some iron filings at it and you kind of see the field lines. It's the same thing, it's just you're using electrons. So we've got again, the kind of magnetite and the non-magnetic matrix here. The outlines of the particles are the same down here. So this particle, this magnetite particle here, where you can see its field is forming a vortex, just like we saw earlier. But when you get particles close to each other, the energy minimization starts working cooperatively. So we've got three particles here that probably individually would not form a vortex, but in cooperation, they lower their energy by acting together and forming a vortex. So we now have this, what we call particle-particle interactions, where the influence of the field of the particles plays a role as well. There's an example on the right-hand side here where we've got these two large magnetite particles magnetized in this direction. So this small particle here is minimizing its energy by actually being magnetized in the opposite direction. Now, I don't have any answers at the moment in terms of how to solve these problems in magnetic separators, but this is something I'm going to be working on. And separator design and configuration needs to be informed by these rock magnetic aspects in order to optimize that function. So getting back to the green steel and this desire to increase the amount of iron, again, remember for green steel production, we need iron above 67%, this red line here. Now that may come over as a slight magic number, but the story gets a little bit more complicated than that, because what you want to do for all of these ores is increase the iron as much as you can. So more iron means less energy is required in the steel production process. So even if you're producing your energy from renewables, you still want to use as little energy as you can. So it isn't simply a case of getting up to 67% and stopping. This beneficiation process, there's always room for improvement until you hit 100%, which of course is never actually going to happen. So this is going to be a continuing effort to try and increase the grade of these ores. So in a lot of places, traditional steel production is stopping. This is Teesside. This is the picture that I showed you, the blast furnace that I showed you a picture of at the beginning. That was demolished in 2022. But British Steel has now announced that green steel is to be made on Teesside. So Teesside, steel making is set to return to Teesside following an announcement that it will be the location of one of British Steel's electric arc furnaces. So the world is changing and moving towards a green steel future. Like I said, there's hurdles, but hopefully hurdles that can be overcome. So to conclude, Australian green steel production is viable based on availability for renewable energy, green hydrogen, and so on. Like I said, there's hurdles. Of course, there's hurdles, but hopefully they can be solved. Beneficiation, in a lot of cases, is going to be needed to make fuels suitable for hydrogen direct reduction. Again, we treat this like some kind of magic number, but we need to get that grade as high as we can. And magnetic separation is going to play a key role in that beneficiation process. And that is crucial that is going to be informed by rock magnetism, which is what I'm going to be trying to be helping with in the future. And like I said, high-grade products require less energy. So beneficiation is always going to have the aim to maximize the amount of iron. Okay, thank you.
Thank you for the great talk. Do we have any questions for Dave?
Thanks, David. It was very cool. I was just wondering, do you know how big the particles will be when they go into like current magnetic separators?
Yeah, so there's two aspects to that. So first of all, maybe if I go through, I'm going to have to go all the way back to the beginning. When they are crushed and screened, you get different size fractions. But typically, the magnetic particles are much smaller than that. So you may have a piece of iron ore that is 1 millimeter, but it's got thousands of magnetic particles in it. So it's then a balance of how that particle is going to behave hydrodynamically in the separator, given its total size, versus how those millions of magnetic particles are going to behave in there. So the magnetic particles are typically going to be like a micron or smaller, even if you're dealing with something that's a lump that's a couple of centimeters. Yeah. But magnetic particle size, because magnetic properties vary so strongly with particle size, that's something we can get a decent handle on.
So one is more geological. Why is the quality?
What, sorry?
Why is the quality of Australian iron ore quite low? And are there deposits elsewhere on Earth where the quality is significantly higher, and that could be used as opposed to having to go through these processes?
I'm sure there are.
But what
So yeah, in terms of the qualities of the ore, this is where I'm going to have to take a bit of a punt. But there are certainly cases where, you know, if you're looking at something in the Pilbara, it may be pure iron ore in terms of it's just made up of hematite and goethite. But goethite in particular is not suitable for in these furnaces. So you need to get the hematite out from the goethite. Sometimes you can put a bit of goethite through, but if it's been aluminium substituted, it's not going to work. So these are the kind of things that, you know, that the engineers are working out. Other places in the world, I'm pretty sure there are, but just not in huge quantities. So some places are already producing green steel. Whether that's through huge amounts of beneficiation, yeah, I don't know, or whether they've got ores of sufficient quality. But based on that export plot, where there's very little above 67%, suggests, you know, beneficiation is going to be essential to actually do it.
I guess my question is more motivated from kind of Australian economics, right? If green steel takes over.
Yeah.
Will it end up that Australian ores are no longer required? Is there enough elsewhere? I don't know.
That I don't know, but from a purely Australian point of view, with it such an important component of the economy,
Yeah.
they've got to find a way to make it work. And I guess, and it is just a guess, this is why you're seeing the government put money in. This is why you're seeing BHP and Rio collaborate on these problems, because they recognize that there's hurdles that need to be overcome if they're going to stay competitive in a green steel market. Did you have a second question?
I think I threw the 3 or 4 questions.
All right, okay. I think maybe there was a question that came up on the chat, but yeah.
Actually, there was a chat question. Do that.
Okay, yeah. We got one question from online audience. The question is, magnetic separation sounds energy intensive, both in terms of the actual communication and then the magnetic. Do you have a sense of the trade-off in terms of the beneficiation process versus steel making with the low quality feedstock?
I don't. I mean, from the magnetic separation, I should close the microphone, sorry. From the magnetic separation point of view, the magnetic component of it doesn't need to be that energy intensive. You know, if you're using rare earth magnets, for example, or simple kind of iron core electromagnets, I don't think it takes that much energy. If you need the case where you need a much stronger field and you're having to use a superconducting magnet, then yeah, that's going to be energy intensive. But I'm sorry, I don't really know about the trade-off between that versus using lower grade or later steps in the process.
Yeah, back on.
You put the last slide up.
There we go.
I wanted to ask about dot point 3.
Mhm.
You made the great case that magnetic separation is needed
Mhm.
to increase the ore, and you made a very clear case that the properties of rock magnetism are important in understanding that.
Mhm.
But what I didn't hear, like you said that you hadn't solved how to do this, but do you know whether it's worth doing, in the sense of how much improvement could be made by using the physics of rock magnetism?
Yeah.
Or do we only know whether it's worth solving the problem once it's been solved?
Yeah, so that's right. The way I've presented it might come over as a little disingenuous to magnetic separator technology that is already pretty effective and so on. What I think is important, that when you look through the literature, the way that these things are being modeled at the moment in terms of understanding how they're going to behave in a separator are, not to be too blunt, wrong, and very wrong. They're based on errors in the literature that seem to have propagated through, to the point where they make predictions along the lines of particles can become infinitely magnetic, or alternatively, if you apply a high enough field, strongly magnetic particles will not be attracted to a magnet. These are some of the consequences of the framework that's currently being used in the literature. So there's certainly room for improvement. Now, like you said, whether that improvement is worthwhile or not, we won't actually know until we try it. Yeah.
We got another question from online audience. We can read this one. Can you comment a bit more on the role of the mineralogy? Magnetite is of course much more magnetic than hematite, and also has a higher ideal content.
Yeah.
72.4% versus 70%. Though magnetics may have additional chemical impurities such
Yeah.
as reaching a few percentage.
Yeah. So this is a point I didn't discuss, but I can go back here. So when you look at magnetite versus hematite, both iron oxides, but magnetite is about 200 times more strongly magnetic than hematite is. This is a quantum mechanical effect of simply how electron spins are organized within the magnetic lattice. When it therefore comes to separation, this means magnetite, you're going to generate a moment that's 200 times larger than hematite, so you're going to preferentially pull out the magnetite, leave the hematite behind, if that's what you want. Magnetite will also, its moment increases more quickly than hematite as a function of field as well. So depending on what you actually want to separate, these are factors that you need to take into consideration. To give another example, goethite is really difficult to magnetize. So people have tried in the largest magnetic field that we can currently produce on Earth. So the Earth's magnetic field is about 50 microtesla. People have produced magnets that will give out fields of 57 Tesla, and they still can't magnetize goethite. So if you want to pull goethite out in a magnetic separator, it's going to be pretty challenging. What you also have is an association between these different minerals that may cause problems. Maybe you want to pull hematite out, but you also have goethite in there that has a small amount of magnetite associated with it. And then suddenly you're pulling out the goethite because the magnetic force is being determined by that little trace of magnetite that's in there. So it's particularly complicated, and that's where we hope, to kind of come back to the question, that's where we hope that having a better knowledge of the rock magnetic properties is going to enable us to come up with schemes that will optimize the beneficiation in terms of what people actually want to get out of it, rather than it simply being you will automatically pull out the magnetite because it's the most strongly magnetic. Yeah.
Okay, I guess we have a last question.
So when you were reading up on the earlier slides,
Mm-hmm.
did you get a feeling for the proportion of CO2 emissions due to the energy generated to run the furnace versus the CO2 emissions from the coal that you add to the iron to reduce it?
I have seen that number, but off the top of my head, I don't remember what it was. No, I can get back to you on that. I have seen it in one of the reports, but I can't remember. Yeah. But I think given, I mean, what did we say in here? That there's 770 kilograms of coal to produce 1 ton of steel. So if you're turning 770 kilograms of coal, well, that's not just heating, because that's the metallurgical coal as well. I'll need to get back to you on that. Yeah.
Okay, thank you all. That's all for today.
Okay.